Hi. So you've been waiting for this, huh? Yeah. It's 4 o'clock we start. So let me first introduce myself. I'm Wilma van Wezenbeek. I'm the director of the TU Delft Library. I'm very pleased to welcome you here at this event. It's the second event in a series. You see it here on the screen. We have a future forward seminar on science in the open era. And I guess the way we are sitting here together, you all are aware of open science. Are you? And we also all, I think, more or less agree it's a good thing. But we have also some questions. And so, should all research be open? How about collaboration with commercial parties? What do we do then? How about privacy? So we had a lot of questions, and we're not saying that we are here to give you the answers, but we would like to entice discussion about these things. So that's why we have started this seminar. So it's the second one, and today it will be on open hardware. So do you have that? Yeah. Oh, so this is... Oh, it's only pointer. Okay. I will. Perhaps the other side? No. Oh. Oh, this is also very nice. The question is, where is this? Any idea? Santa Monica, is that okay? Sorry. Oh, where is it?
It's Brighton, actually. Oh, wow. Yeah.
So that was a teasing question. We did it on purpose. Yeah, really. So I already explained why we have these sessions, and the idea is that we, and it is good that we are with, not a lot of people, so it's comfortable, I guess, to ask you questions, to intervene. I think you won't mind if we would do that, and that also we not always agree on things. That's okay. That's okay, because that's actually the way we can grow. Huh? We don't agree on things. We do this. We try to do this seminar every second month, and we not only have a talk, we also like afterwards to have a sort of network meeting, so discuss things together. And just practical notes, as you might already have noticed here, we have Jan, who's making photographs. We have Thijs there, who is recording, and we also afterwards will do just a few quick interviews with anybody who likes to do that, just to have some variety, I guess. And are you all okay with that? Yes? Okay, thank you very much. And then before I hand over to Andre here, when Marta mentioned, because Marta here is the big organizer, when Marta asked me to do some opening remarks, and she mentioned that the topic of today would be open hardware, it suddenly reminded me of something, and it was hidden in my memory. But we did a few years ago, it was in 2015, did some research together with Demo. Demo is also a supporting service of the university, and lit research to open labs, virtual labs. And we ended there, so we did a lit research. But I thought it might actually be nice to tell you just a few things about that. Because for me, open science is, of course, opening up science, but I think you have to approach the topic of open really holistically. So open means also that I want to be an open person, that the spaces that we have in the campus are as open as possible. So open in all its appearances. And so with my colleague of Demo, Gerrit, we discussed about the fact, what can we do with our labs, with our facilities? And then we found that you have virtual labs for education and you have virtual labs for research. And I will not go through everything now. So I've made some links in this slide, and I know that we will share the slides later on, so you just can click on it. But so for education, we found the Open Science Lab from the Open University. And I checked, because this was 4 years ago, but they're still there. They have some top experiments on remote nitrate measurement, I think it was, and some virtual field lab trips. So just for students. And we also investigated, of course, what's out there for research. And then we found a few. And I think I listed it here. It was, I guess, a mixture of things, of elements that are perhaps related to what you will going to talk about. So already we understood in the TU we have a catalog of lab equipment. But there is also an international marketplace for that from the UK. And you have something from Monash called My TARDIS. At that time there was sort of possibility to hire some instrument time from that site. And of course we have our own Zandmotor / Open Earth project where you can make data products out of open source, of raw source data. And there is also from Australia this biodiversity, climate change, virtual laboratory. And then you can do some modeling, some visualization. So we ended there. And because it really was somewhere lost, so I promised Marta I will give the document and we'll probably put it on our open working blog so we can share it with you. And now I think I said enough. So I'm very interested to hear from Andre what his projects are about. You are, I just asked you because I didn't know what it was. We're a Fries Wiesent fellow. I now understand.
Yeah.
And you're very much into open science. You're an open science advocate. And I think you better can perhaps tell a bit more about yourself to the audience now. So give Andre a hand. We will listen to you.
Thank you. Yeah, but I just need the clicker. Yeah, thank you.
It works.
Yeah. Let me just set up things here. So, great. So, the slides, the presentation is already available. So please don't mind copying any of the links or anything. You can get all the slides directly from this link. If you're a little bit skeptical if what I have to say is useful or not, this will come again at the end of the presentation. Maybe by then I have convinced you. Yeah, and yeah, so let's maybe dive into it. So designing open hardware for the 21st century science. First of all, I would like to say thank you very much for the invitation. Thanks for receiving me. It's been very nice so far. Also, I'd like to say that this work is not based solely on my work, but it's the collaboration of many, many people across the world. So everything that I say, keep that in mind, because without the support and this open collaboration between all these people, none of this would be possible. And just a little bit of an overview of what we're going to talk about today. So I'm just going to talk a little bit about really briefly, how I got involved into this project, a little bit of an overview on how research is funded, and then we dive into the questions of why should we be advocating for open science, why should we be using open tools, and why I believe that open science or open hardware for science is a better way to develop things as compared to proprietary and patented and intellectual property tools. Then we're going to see a couple of repositories and the communities that are, or some of the communities that are involved in this space. And then we're going to open the floor for questions. Okay, so a little bit about me. I actually studied biology and neurosciences, part of it in Brazil where I'm from, a part of it in Germany. And for a number of years now I've been advocating open science. So for me it all started with Open Neuroscience, which is a little portal that I putting together projects that are either free or affordable or open source for neurosciences. This has now 4 or 5 collaborators, and we're trying to curate this in an easy way for people who are interested in neuroscience. which got me to collaborate with Trend in Africa. And we've been developing tools and trying to teach researchers in the African continent how they can use open source tools to build their own tools. The idea of teaching not a man to fish, but how to build fishing rods. Not every lake is the same, and therefore they need to know what tools they need to build their own tools, right? I've been editing together with other people the PLOS channel collection for open source tools. And this last year in 2018, I began these 2 fellowships where the idea is the same. Can we ask researchers around the world what are the needs that they have in terms of tools and laboratory equipment? And once we know that, can we actually build based on that demand so that we're more effective with the tools that we're building? I also work at the Baden lab building tools for the lab, and which are open tools, of course. And recently this year, I actually started a project together with Karin Heinck, which is to set up a company where we're building open tools, open scientific tools as a service, right? So you could take this as I'm promoting my own company, or you could see this as a guy who believes so much in this idea that is willing to put his life sustainability into that idea. I'm not going to talk about this company very much because this is not the focus today. We want to learn about open hardware and why we think it's better for science in general. So this is just a note that you know what's going on. Okay, so a little bit of an overview. I think everybody's familiar with this, right? But just that we are in the same pace. All we do is paid with taxpayer money, right? People pay their taxes, it becomes a grant. Then if you're lucky enough, with a lot of effort, you write a grant, you get some money to do your research. And then if you put more effort and a little bit of luck, you can get out of this research some publications, like probably new drugs, new treatments, new technology. For me, this is where our whole problem starts. Once you get all of these new things and you're inside the university, universities don't have the capacity, or should they be aiming to bring this to the public, right? We're producing knowledge, not commercial tools necessarily. So the way this normally happens is that then the university patents or sets a copyright to this idea, which is then transferred to a spin-off, a startup company, or to an existing company, and they have the sole distribution rights of that new knowledge. And this is already, for me, morally debatable because it was all paid with a community effort, and now it's in the hands of a very few people. Market logic, high costs, and again, very few people are able to access these things. Right, keep this in mind a little bit. We're going to switch gears a little bit right now. Why open science? Right, so here I'm just showing 2 examples why I think we need open science. These were 2 reports that came out from major replication efforts that pretty much failed. And it's interesting because I just saw that you have this invitation for the next talk, and it's actually about replication. So if you want to learn why this is very important, you can come and learn about this. But basically, this is showing that even when we're doing our best work and trying to put everything as nicely as we can, our research is still not replicable. So you cannot replicate the results that we got in the past. This is troublesome, right? Because this is the cornerstone of science. You found something over and over and over again, and this is then likely to be true or to indicate you in the right direction. Another thing is that not only that, but even the most high prestigious journals are letting things out that are not necessarily correct, right? So this came out in 2016. There was this paper that debated that there was a limit to lifespan, and the statistics were completely flawed, and people debated this very much. And basically this is what I'm showing here, is a piece of somebody who analyzed the case and basically discovered that, well, Nature asks reviewers to look at statistics if there is time available, which seems very, very wrong from the point of science, right? So this is because how the system is set up. On top of everything, the companies that are then supporting science by editing the papers and getting these things out there are basically making so much profit out of this that they're in the same range as banks, pharma companies, and car companies. This is a study from 2015 showing that, you know, like these huge 30% profit margins are made out of public money in the houses of several millions of dollars. per year, which is a little bit obscene in my point of view. Somebody calculated this means that in Germany alone, each paper that is, produced costs in between 3,800 and 5,000 euros. Sorry. And so I think this is a little bit of a historical background why and how this whole open science movement started, because it started, as far as I know here, with the publications and how our results are coming out and how these things are published. I'm not here to talk about this today. This is just to set the mood on why this whole thing started. Right, actually, and then again, just a little bit overview why we need open science. So open science, we're going to see, is going to make things more reproducible, more robust, more accessible, affordable, and accountable. So in the end, for me, open science means better science. Luckily, there are several initiatives already taking care of these publication issues. And as I said, I'm not going to be talking about them today. But this is just, if you have the slides, you can then go look for them on Google. Yeah. And so we can now shift gears again to open tools, which is basically what I want to talk about today. So in open tools, we can start thinking about software and hardware. If you think about software, you would say, okay, software is great, right? It works, and we don't think about it. This is a paper that came out in 2016 showing that there is a widespread error in the names of genes that are published in journals. Basically, the problem is that because people are using Excel, and Excel is not made to take gene names, it converts the names into a number and then reconverts again into another name, and in that way, the names get mixed up. The problem is big enough that basically what you're seeing here is that basically 30% of the papers in supplementary files, 30% of the papers in Nature have errors in the supplementary files, the spreadsheets containing the gene names. This could be as silly as changing like the last letter and then people realize right away, but it could be as serious as I spent my whole PhD searching, going after the wrong gene, right? Which we can all agree is a bad thing, right? And then enters the idea of open source software, right? These are just two examples which are at the very are the very latest examples that I'm aware of on how people are creating code and generating code and making their data reproducible. So here on the bottom left, you see Jupyter. And Jupyter is basically an environment where you can code in several different languages. And you can do it actually step by step. So you can make a notebook out of this, which is called. And then basically you can teach people step by step what your code is doing and write comments and show them exactly what's going on. Not only that, Jupyter is now making code in between different languages interoperable. So basically you can start programming a certain language which is good for a certain thing, and then if you need a statistical package from another language, you can pull that in, do that statistical analysis and bring back to the other language and basically pick up the strengths of each programming language into one environment. And then somebody did a one-up on that, which is basically Binder. So Binder is a server system where you can store together your data and your code, and basically people can execute this via the browser. So basically you can publish your paper, all the data is online together with the code, and people can, as soon as the data is published or as the paper is published, analyze your code, run the code that you ran, change parameters, play around with it and see what happens. Right, so this is of course much more accountable. You can see line by line what you're doing, learn from it, and actually reproduce everything. Is anybody here has never heard the term open source? I mean, that's okay if you haven't. So just 1 minute for us all to master open source. The idea is that everything that we create, its code, its hardware design, protocols, even cake recipes, are freely shared via using licenses, right? So there are several different types of licenses, and you can use any means that you have at hand. You can use the internet, USB sticks, recipe notebooks, it doesn't matter. The idea is that you share your knowledge, you share information so that other people can use it, remix it, improve it, and bring it back to you so that there is this environment of information going in all directions. Basically, we've always done this, right? Right now, we just have like a fancy name and certain protocols so that we follow a certain standard, which is good. So in case you don't know, your smartphones, your data centers, the supercomputers, computers in airplanes, everything runs open source software. There was a survey from this link, from this study, that showed that 78% of the companies in the world run on open source. Less than 3% of them don't have any open source code at all. And basically this means also that these companies are relying on this infrastructure, and we're going to see in a bit how this is commercially commercially interesting. But basically the whole world runs on open source, and why aren't we in academia then running on open source? Why are we relying on these tools that the rest of the world is already relying on? So now we finally get to the point. Scientific equipment. Is open source hardware better or not? I would like to start with an anecdote that happened actually this week in the lab. So we have one of these in the lab. This is actually a pump that basically allows for the flow of a certain solution in our perfusion chamber, right? And we have this exact model, and this broke. And this was a super quiet pump, and it got substituted by a very noisy old one that we had spare in the lab. And I got super annoyed because I'm sitting next to this thing the whole day, and it's being super noisy, and I see, okay, let me see what this thing is so that we can order another one, see what company it comes from and so on. So I found, I'm not going to say which company it is, but basically I contacted them and found out that they take in between 8 to 10 weeks to ship me one, and it costs 750 pounds for this pump. Right? 8 weeks of this noise on my ears would be devastating. So I went to look a little bit closer since I'm already building hardware in the lab. And then I flipped this thing upside down. Can you read what is in the black? So it's basically an aquarium pump, right? And if you go on eBay and you find a very similar model, you can get the same pump for 8 pounds. It ships the next day, it's in the lab, right? So of course, none of this is open source hardware, but this is one of the reasons why hardware should be open, because honestly, as consumers of open hardware for science, it seems we're being taken for fools, right? We're going to see the other advantages of open source hardware in a bit, but this is like a very good anecdote why we should be always questioning, always saying, is this correct? Is this the best what it could be? How can we make this open? Right? So let's take a more classic example. So this is what you can see on the left figure is a microscope from 1940, I think. And as you can see, the one on the right, it's a very modern microscope. It hasn't changed that much. The idea is the same. Some glasses in form of lenses. You amplify what you want to see. You have a light source. Maybe if you want to do fluorescence, well, one step back. It didn't change that much, but you still pay 5,000 euros for one of those, right? It's technology from the 17th century. Of course, it got much better over time. But still, it's very expensive. If you want to do something like fluorescence, which is like one of the working horses of biology labs, you need to pay another 5,000, right? There are no more patents for this. And still, this thing, because it's so expensive, I wouldn't dare open it up myself and try to repair it in case something goes wrong. So I'm basically tied to this company that sold me this thing, right? Then it's also hard to customize. If I found out something that I want to do a little bit of a different fluorescence, I can't because this one model specified for this fluorescence, I have to buy more add-ons and so on. It's also designed for the major markets, which are Europe and the US and Japan, right? You would say, that's fine. What could be different in other places, right? Coming from Brazil, having worked in Africa, I know that the conditions are completely different. So you need something that is not as heavy, that it's battery powered, that doesn't need to rely on mains electricity all the time. And you might think, yeah, come on, that's silly. But we're not talking about televisions. We're talking about tools that generate knowledge, that generate treatments, that can do diagnostics, right? So this is important. So can open hardware be better? And so together with Tom and Lucia and some other people from Trent, we actually started playing around with this idea of building a cheap microscope, right? So we published this paper, and this is to say for the researchers out here, developing open science hardware is not a career killer. You still get your publications out there. This was luckily enough for us, like highly cited. And basically we showed that with $100 worth of equipment bought from China, you can actually build a microscope that does fluorescence, does optogenetics, and a bunch of other things. As I said before, we're not the only ones. And this is another advantage of open source hardware. There is diversity. and a resilience in this, because if tomorrow the knowledge about the microscope we build disappears, you have other tools that can be used, can be adapted, can be shared by people. So here basically I'm showing you 4 different models, and what the point that I want to make is that each of them have different capabilities. So for instance, the one on the very left, the yellow one, you can actually use to see even all the way down to malaria parasites. So these are really tiny. The one next to it is the one that I just talked about that we published. You can do fluorescence and optogenetics, which is a fancy neuroscience method. The one in the middle is actually very good if you need to automate things. And the one on the right was actually developed by these colleagues and friends in Chile, and it's very good for fluorescence with bacteria. So what all of them have in common is that they are somewhat portable, you can drive them with batteries, and they're easy to customize because all of their building plans are available online. Not only that, they have all been published in peer-reviewed journals, so they follow the gold standard of academia. And because they're much more affordable, can you think about not having one tool in the lab, but several of them? Could you, instead of having to book, things overnight because the lab is completely crowded with people trying to use this one equipment, have several of them so that people do things in parallel? Before I delve into this other part, so far so good. Are there any questions or comments or anything?
So what with open source software,
yeah.
With open source software, you obviously need developers to keep it going. Mm-hmm. So what kind of extra staff requirements do you need to keep this type of infrastructure going in the lab that may add to the costs?
Right. So one thing that I didn't say, which is a little bit of a secret in the industry, is that hardware is now software. Right. So all of the things to create this require you to have, for instance, a 3D printer, but the files to generate the parts are software. Right. So the idea is pretty much the same. All of them are in a GitHub repository, where you have all the files and all the instructions on how to print them, how to put them together, and so on. So once they're published, if the main developers don't want to keep developing in it, the community can pick it up and develop as open source software, or as if you would open source software. Okay, so the other interesting thing is, because these things are now so cheap and all the designs are open, can we teach other people to do it? Right? Can we distribute this knowledge? And this is something we've been trying with Trend for a couple of years now, and we've been doing workshops in the continent where we've been trying to show researchers how they can use available local tools to build their own equipment and leverage this whole open source movement to actually contribute and build the tools that they need. We've been trying, there was a lot of trial and error on what was the best method to do it. In 2017 we had the first project-based project where people came with the question with a project that they wanted to develop for a 2-week long workshop, and in 2 weeks we were able to bring them from not knowing how to code to learning how to build and operate a 3D printer, do some Arduino programming, a little bit of code, and then because they came in teams, they're able to support each other once they go back to their home institutions. Right? This was very nice. And last year, basically, I think, struck a nerve, which was we got people together and we fine-tuned all of these trial and errors that we had, that something that was started there during one of these workshops was actually published in a peer-reviewed journal. So this is now technology from people from Ghana, developed by people from Ghana, in Ghana, for like the local or maybe the global community. Right, so we've been debating with them quite a lot. Can we make a business out of this? Can you guys be the first suppliers of open science hardware in Ghana and try to bring development not by outside in, but from inside out? Right, so how can we basically encourage and try to help these communities so that they basically bring themselves up by their own boot, so to say, right, and create development where they are. Yeah, so this is a little one that I'm especially proud of. Okay, so open source hardware, right? We've seen that it's much more affordable. You can use for education. You can use to capacitate people to kind of solve their own problems, right? Now we shift gears a little bit again, And I would like to ask you, who knows what this is? I think here in this faculty this should be quite simple. Yeah?
Yeah, it's the Prusa printer, the first successful commercial open hardware 3D printer.
Exactly.
The most widely used in the world.
Yeah, and so that's a very detailed answer. Thank you very much. But I was going, so that's absolutely correct. My point here was this is a 3D printer. Can somebody tell me why 3D printers became so popular? Yeah. Yeah.
All right. Well, it's something interesting. After the patents expired, immediately, the humanity had to wait 20 years for the patents to expire, and immediately the citizens and especially scientists I think in England started the RepRap project, which is a 3D printer to print and replicate itself. And the thing is that after that, the explosion of innovation was much faster, much richer than the traditional old technology development approach. So it's a change in our era, yeah.
Yeah, exactly. So this is absolutely correct. So the patents expired in 2009. The project from the RepRap started in 2007 inside the university. As soon as the patent expired, this thing exploded, right? Because they already had covered a lot of the ground. And in 2018, the 3D printing market was a $14 billion market in the US alone, right? And the reason why I'm saying all of this is A, patents are killing innovation the way they're set up nowadays. And this is not the only case. There are several cases and we can make a case for this. And B, once you have 3D printers, they spin off to a lot of different tools for the lab. So what you're seeing here is that the point that once you have the technology for 3D printers, you have the technology for syringe pumps. What you're seeing on the left is basically this animation where we have two syringe pumps. One of them is like filling the syringe and putting it back out again. This might not seem like much, but if you're working with cell cultures, part of your day, and a lot of it, a big part of your day, every day is to exchange the media in the cell cultures. If you have an automated system like this, you're free to do other things, right? And basically what this is just take one of the axes of the 3D printer as it is and put it on the tabletop and put some tubes and a syringe on it and you have a syringe pump, right? So because there was this boom and the technology evolved so fast, now you are expanding to other places where you weren't. So open source enables innovation where you didn't think it would be, basically, right? Another thing that open source makes, or that the 3D printers made robots easy. So the field developed so much that you can now build robots as easy as it can be. Of course, you need a little bit of knowledge, but there are these projects online, right? So the one on the left is basically a media filler. So basically it takes media for fruit flies and puts it in all of those little vials. The other one is a liquid handling robot, the middle one, for cell cultures. And the one on the right is also a liquid handling robot that basically is used for pipetting and doing molecular biology protocols. This one is from a company called Opentrons, and it was a 2014 master thesis project in New York. In 2015 they run a Kickstarter campaign. In 2016 they were selected for the Y Combinator, which is the biggest startup accelerator in the world, I think. In 2017 they began producing their second generation robot, which is this one you're seeing, and in 2018 they raised $10 million for venture capital to make this thing work. My point here is that it's great for them, it's great for the community because it's open source, but it also shows the point that open source doesn't kill market possibilities. So this idea that you need to protect your only idea in the world with a patent and spend all this money and so on has been killed by this example. If it is the only example or not, I do not know. This is still very recent. I think we're seeing history as it develops, which is quite interesting. But this is not the only company that is selling open source hardware, right? So you have SparkFun, Adafruit, FarmBot. They're all companies who are thriving for, some of them more than 5 years now, selling open source hardware. And so one comment here, which I think is quite interesting, if you look for TED Talk and SparkFun, you're going to see the CEO of this company talking about why they use open source and what kind of generation cycles they have. And basically he says, well, we have 12 weeks in between launching a product in the market and being copied on eBay. and we're still a 120 employee company who's worth like more than 5 million revenue a year. So they seem to be doing all right. Another point for open hardware is that it really has the ability of bringing massive data collection to the world, right? So this project is called Safecast, and it started with the Fukushima disaster in Japan. So what you're seeing here on the left is the device itself is about this big. You can buy it from them for like $500, or you can buy a kit, or you can buy the part yourself and build it. But basically what this is a Geiger counter that is connected to the internet, and it's connected to a database. And so what you're seeing in the middle is the map that they generated for radiation right after the Fukushima disaster. And what you can see in the hotspot there is basically the region around the power plant. And if I'm not mistaken, the green circle was basically the area that the government was planning to isolate. And as you can see, they needed to isolate a much bigger area, but they didn't have the data because there weren't enough Geiger counters available. So what happened was that Safecast came and said, hey, government, we need to properly measure this, right? So they made a collaboration with the post office, and then every post car or delivery man had one of these in them. And these things is then sending data as you're walking with it around, right? So as you can see on the graph, basically in July 2016, you had more than 40 million data points for radioactivity. And what I would like to show here that I couldn't put on the map was this. So basically this is how this project evolved. So you can see that people started buying and walking around with these things around the world, and now we have like a much better understanding of how, I mean, it's not complete yet, but it's much better than we had before from what radioactivity looks like around the world, right? They actually launched recently their second device, which is an air monitor, an air quality monitor, and we should be getting data out of that as well soon. Yeah. So again, this is something that wasn't so far possible with the traditional methods of data collection. As I mentioned, yes, there are several companies appearing, selling or providing services around open source hardware, and a lot of non-profits as well. These are just some examples, but basically you have OpenIFES, which is doing electrophysiology for neurosciences. You have IO Rodeo, which is doing basic biology tools for the labs, and many other. Right, and some of these companies are now more than 5 years old, which shows a certain degree of sustainability. And even if they went bankrupt, because everything is documented online, you're not an orphan of that tool anymore. Right? This was actually how the CERN, or one of the reasons why the CERN started collaborations with companies, in the sense that all of them had to produce tools for the CERN that were open source. Because the CERN is a project from several different countries that is worth billions, and it's probably going to outlast many companies. So they didn't want to be orphans of a certain tool in case that company went bankrupt. So everything that is built into the CERN is basically open source hardware. Right? So they're actively working on creating licenses and creating an environment for open source hardware inside the CERN. Yeah, these are just other examples of open science hardware. Some of them are published, some of them are hobby projects. I mentioned this one, which is the FarmBot. So basically this is a 3D printer, so to say, a numeric control machine that you can use to automatically grow your own vegetables in your garden. Right? So if you're thinking about food and food safety and how healthy our food is, you could think of this as one possible solution, as it automates a lot of the things in a distributed way. There are many other examples. Yeah.
Gel electrophoresis equipment.
Which one?
The lab. The
on the very top?
in the, so the top, middle.
This one.
Uh-huh.
This is an electrophoresis chamber, yeah. So this is also documented online, and you have several power sources for electrophoresis actually available that you can build. But be careful, because these are really high voltage power supplies. Yeah, but all the documentation is online. One that I like quite a lot is this one here in the bottom, because these are basically Raspberry Pi computers set up in a cluster, and they're built using Lego parts as a frame. So it's quite a neat project if you want to teach students in an undergraduate course how to program parallel computing, right? Because they are super cheap, but then you have like 64 nodes, and then you can teach them about parallelization in computation using Raspberry Pis. If you use the Raspberry Pi Zero, which is $5 each, then this is not that expensive at all. Of course, you won't discover the next integer of pi, but still you can use it to teach people how to, do distributed computing. Many other projects. This is just a little bit of it. I hope that by now I have convinced you that we're living the Cambrian explosion of open hardware. So if you go into Wikipedia, there are more than 70 projects that are open source hardware, right? The only issue there is that they are already at the commercial level or the big projects, meaning it's not even like grasping the diversity of tools that are available. Right, in these slides there are another 36. There are many other repositories online we're going to see. And I hope that I also convinced you that, or this I'm going to talk about later, sorry. So what I'm trying to say here is that this Cambrian explosion is happening because the tools that we have to create hardware are getting better and easier. So you have 3D printers that you can easily design something, print it, an hour later you see the design didn't work, you change it in a file, you print it again until you get something good. So you can do all of this fast prototyping. The price for manufacturing is also dropping. The internet infrastructure to share tutorials, videos, documentation is getting much better. And as I said, some of these companies seem to be here to stay. I hope that I convinced you that you have traditional and OS systems, and that there are several advantages of using open source hardware, right? Mainly that you can adapt and change and know exactly what they're working or how they're working, and know that you can adapt them to your local realities, as opposed to these traditional ones which are normally more expensive. You are locked into one supplier, they're hard to fix and customize, you can only have one per lab because they're so expensive, and so on and so on. Okay, so now about communities and where you can find more information. I'm sorry if this is a lot of information, but I thought we would give you like a nice overview. And I see that I forgot to add here on the editors the name of the last person who was in the editors, and this is terrible. I'm sorry. Yeah, I mean, I'll change the slides later. Blooper. Anyway, so we're creating papers and other interesting projects that are open source software and hardware for academia. And there you can find a curated selection. So easy to find place for these tools. And a little bit about this project with Mozilla that I mentioned is basically we wanted to change this dynamic of, like you start a project. So we started with a microscope because it was something that we needed for the projects in Africa and so on. But this was the need of one lab in one department inside one institution. And so basically the question was, can we map what researchers need and basically build open source hardware based on that map, right? So if you figure out that out of 100 people, 50 of them need microscopes, let's build the microscopes first and get them to a point where they are the same or better than the current commercial available solutions, and move on to the next thing. So there is an online survey going on. So if you can please share this with your contacts. It's actually, we're ending the survey by the end of this month, because we are going to enter phase 2 of this project, which is actually seeing what are the most demanded tools and actually building them. So during the months of May and June, we're gonna, in a distributed way, get communities to build, each community one of these tools, and have everything set up as a repository that everybody can copy and improve on it. And so basically these are the seeds of the prototypes of this demanded hardware, right? Of course, comments, contributions, and suggestions are more than welcome. And I don't have it here because we didn't launch the call for participation yet, but this is coming out later this week. And as soon as I do, I can send it to Marta, and Marta can send it around to the networks here. Yeah, and this is what I've been doing together with Mozilla and the fellow, the Freies Wissen project. So thanks to all of these institutions for supporting this project. And I think one of the last things that I want to talk about is the GOSH community, which is also a community that has been supporting hardware and open science hardware for a number of years now. And it's an amazing network of networks. So basically, the idea is you get these people who are already engaged in building hardware, and you get them together once a year to see how you can answer this question. How can we make open source hardware the norm by 2025? Right? From these meetings, a roadmap showed up. So you can find this online and read the roadmap. There is a manifesto showing what GOSH is all about. And what I think is really interesting is that in 2017 we had a meeting in Chile, and it was one of the most diverse meetings that I ever been to, where more than 50% of the participants were from low DGP countries, 48% of were women or people who are non-heteronormative, I guess we would call it. 25% of people of color, 34% from NGOs and community groups. Right, so this leads to a very enriching experience and talking about what the needs are, where do we need to take it, what needs to be respected, and how can we move forward together as a movement and not just say, okay, Europe is going in that direction, and then the guys in Africa are going in that direction, and then the people in Latin America are going in that direction. Obviously, we learned that there are differences that are not easily transponable, and this is why also local meetings started. So actually today, I think it started yesterday, the Africa OSH meeting is taking place, which is the second edition of the Open Science Hardware meeting in Africa. So it's basically people who are in the continent already working with this, getting together to find solutions to their problems. There is a very, very nice forum online, so if you Google for GOSH Community Forum, you're going to find a very receptive, very diverse online forum where people are debating issues and talking about things that how they can help each other. So I would really recommend that. These are some repositories. I don't want to go through all of them because it's just for your information when you get the slides. But interesting, there is the Journal of Open Hardware and Hardware X, which are two academic publications dedicated to open hardware. Okay? With that, I would like to say thank you, leave my contact information, and open the floor for questions and discussions.
Thank you so much, Andre, for your inspiring talk and all the different examples of what we can do with open hardware. I have to say I was really impressed. I did not know that it's so diverse and there were so many opportunities. And I suggest we move to questions. And Nicola agreed to not to kill the people as I would do with the microphone. Any questions? Comments?
Thank you very much. That was a really inspiring talk. Thank you, Andre. What do you think the biggest obstacles are, or things that are going to get in the way of your ambition to embed open science hardware within science?
That's a very good question, because I think we're still kind of flying under the radar of, you know, people who would be angry that these things are coming up. So I'm guessing that we might find resistance from people who are already building hardware for science, but are not, you know, agreeing with this idea that everything should be open, because this really changes how you should supply a service, right? The other thing is that we need to make sure that the users feel that this is not just like a hobby project, but rather like a piece of hardware that I take out of the box, put it on the tabletop, and it simply works, right? In a perfect word, this would mean I don't even have to know that this is open source, right? Yeah.
Yeah, thanks for an amazing talk. I was wondering if I could push this a bit further, because with the whole open science and open data, we're slowly starting to realize that putting text on paper and downloading it as PDF might not be the way science can be distributed. So you see data sets getting DOIs, you see software becoming published in journals. Could this be the next step, where my PhD could be about making this machine and not having to write a thesis, but getting a DOI for it? And
You mean if we can make this tractable, traceable with a DOI, or?
Think about it, like, if I'm a scientist, I'm getting typically measured on things that grant agencies like,
Right.
and these are things that are citable.
Mhm.
That's the thing that
Right.
we do. So could we make machines citable? Can I make a contribution and just like I would put out a data set, which is the novel thing now, or put out an open source piece of software, which is a bit more established, can we start to put out equipment as scientific output? And is it actually science, or is it engineering, or is it technical support? What's your view on that, basically?
So I think because we are dealing with things that need to be calibrated and we need to know exactly what they're doing, optimally you're going to have a paper describing your hardware so that you know how to calibrate it and what the capabilities or not are. But there is also the possibility of having a repository and giving a DOI to this repository. So if all of your hardware is there, the description is there, then you can make that citable, right? But I don't know how much adoption you get from the scientific community, because I guess in the end they want to see at least a very, very nice description of this. And currently, this is still a peer-reviewed paper. Not to mean that this will be something else in the future, but right now I think this would still be the way of combining both words the best way. Yeah.
Andre, well, thank you for the talk. And if I see the different types of products that are made in the open hardware, what do you think are the most important design principles of a piece of open hardware?
Documentation, documentation, documentation. It's like, how do you reproduce this? How do you get, you know? Of course you want, like, optimally you want this to be easy to source and you can get it in your way and you can easily modify it. But this is also not always possible. So if you have like a very good documentation of this, explaining why and how and so on, I think it saves everybody time, and it also makes it easier for somebody to say, it's not possible over this way, but I can go like that, right? So I think the best design principle is document it from day zero.
I had a question about working with governments, because in my field actually we find it quite easy to convince industry to accept open source things.
Okay.
But we've had a lot of trouble with government where they need things to be standardized and that kind of thing. So what's been your experience with open hardware?
Right, so I unfortunately never had the experience of working with the government open hardware. What I do know is that there is a group in Germany, it's also several people from different communities working together to get a standardization for open hardware. So a DIN standard for open hardware. So they actually already contacted, I don't know what is it called, the institute that does this standardization, but they are back and forth in conversation, both happy with the idea of creating this for open hardware. So it might be that it's still not there, but hopefully in the next few years, there will be a standard for the industry.
Thank you very much for your talk. Are you in any way, say, working with, say, open source ecology, where they're trying to develop open source farm equipment, from the ground up manufacturing, going as far as to not relying on existing industries to extract materials as to developing their own hardware to even do that?
So I know of the project. I never worked or contacted them, but I know that this project exists. I don't know. I think they started in Germany as well. No, someone, US, yeah, and then yeah. So, but I don't know in which state they are. Do you? I work with them. Right. So here. Yeah. Yeah. So one thing we didn't mention. So Jose is here. He graduated here, and is working with open source hardware. So I guess like this is a good person to talk to after I leave tomorrow, because he's here and he's working already with a lot of communities. So by all means, I think you wouldn't mind, right?
Yeah, of course not. Yeah. We're also trying to collaborate.
Yeah. Exactly.
I had a comment or a question about the first.
For comment and question, you get to have the mic.
Yeah, thank you very much. About the start of your conversation, where you had the grants and the tax and stuff.
Right.
Because that's something interesting to go again towards. And my question and comment as well is that there is there a contradiction, a systemic contradiction in the traditional way in which this flow goes? Because what we're seeing now is that there is an explosion of peer production tools. So traditionally we go to a grant and we go to this flow because in order to reach economies of scale we need the companies. But
Right.
now we have these local fabrication tools where we can do things locally.
Mhm.
So it means that we can reach economies of scale in the lab itself. We don't have to go to another country to produce things. So
Mhm.
how this actually changed dramatically the supply chain of things and the cost of things, and how can companies, traditional companies, be competitive in this context where you can probably have your products and the fabrication tools on the spot, you know?
Right. So if I was the owner of a company that is already established in the market, I would say we need to jump on this right away, because this open up market opportunities in places where you didn't have before. So the case for Africa, for instance, we know of labs that get grants to buy like this very expensive equipment, and it stops in customs. When it gets there and it breaks, it never gets repaired because they don't have any local people to repair it and so on. So if I was a company, I would, like established company, I would then definitely try to join this, right? Because indeed it's true that you can locally source things. For the supply chains, I think right now we're not at the stage yet where the complete supply chain is local, because everything still gets shipped from China, right? So
Yeah.
all of the components to build these local tools are still in China, right? And there are people that we know of that are trying to figure out ways to even these electronic components, which are the building blocks of these things, they're trying to see how they can produce them locally, right? With this idea that you don't have this drain of like money to China and parts come out, but rather you have like more circular,
value chains,
localized things
Yeah.
locally. Yeah.
What about the fact that there are so many universal machines that can make other machines like the 3D printer, but there are also CNC plasma cutters, routers. How do you think? I mean, how do you think should the supply chain and the industry go towards sourcing these kind of products to make products, or being with the same scheme of shipping products? Yeah.
I don't know. I think this is again one of those, we're seeing history as it develops, right?
Yeah.
Because the 3D printers were the first one. Now we're seeing printers that are able to use laser to melt metal, and if you get this to a level, then you can actually produce CNC machines. And, you know, like this is gonna. I think we're really at the very like beginning phase of this explosion. So I don't have a comment on how the supply chain should be. Sorry.
No, it's good. Thanks. Thank you very much.
Thank you.
Do we have any other questions? We have time for one final question, if anybody has a pressing question.
Can you send it? Yeah.
So if we wanted to kickstart this within TU Delft, what would you advise as the best way that we could help your movement?
Sorry. So if we want to kickstart this here,
in a particular university, right? What would you advise is the best way to try and get that going?
identify the communities which are already locally doing this, because I'm pretty sure there are many around you, and this is one of those things that it's kind of invisible to the eye unless you're looking for it.
Yeah.
And give them space and time to do things. So the things that we did in Africa was just that, right? We didn't come there with a magic wand and so on. We just told people, look, what do you want to build? We're going to come here and just have like little bumpers around the road that you don't get all the way sidetracked.
Yeah.
But it needs to come from like these little communities that already exist. And thinking about a university, it needs to change. It makes much easier for the students to feel comfortable if it's a policy, not a policy, but if it's seen with good eyes.
Yeah.
Right? If they're not hammered on the head, you have to patent from day one.
Yeah. Okay.
But rather you need to open from day one.
Yeah.
And then if you want some information like about like this work in open, there are several tutorials and things online and things like that as well.
Okay.
Right.
Okay. Cheers.
Thank you very much, Andre. And I think
You're
it's a lot of work to do for us at TU Delft, starting from identifying the right communities, I think. So thanks so much for that. Thank you again for your talk. And I would like to ask you for applause, Andre, again.
Thank you.
Thank you. I would just like to say that the slides will be available, as Andre has already shared them anyway. We'll put them in a repository so that they are persistently available there. And we'll also make the recording available afterwards together with the photos. And I would also like to thank everybody who have contributed to this day today. Thank you for the organizers, Paula, who is running away. Thanks so much for helping us organize. Thank you, Wilma, for doing the opening remarks. Thanks so much to all of you for coming and asking very interesting questions. Thank you, Nicola, for having the microphone and doing the proper throwing without destroying anybody or anything. And I would like to also thank Jan, who has been taking photos today, our Collegerama colleagues who have been recording the video, and also colleagues from the New Media Center who will be recording some interviews afterwards. So thanks so much for this. And with that, I would just like to make a final remark that we have indeed a future upcoming seminar on replication studies. So if you would like to follow up on Andre's invitation, how to make science a bit more reproducible, our next talk, which will be on the 19th of June, so you can have the adverts in here, the postcards on the side, they give you the invitation and the links to register. That's actually a researcher from TU Delft, from the Faculty of 3ME, who is doing a replication study of a paper from the 60s from Science. And basically what that paper in Science has showed that if you are excited about something, then your pupils in your eye widen. So he tries to see whether it's actually correct or not. So I think it will be an exciting talk. If you would like to see the outcomes of his replication study, see you in 2 months' time. And without any further ado, I would like to cordially invite you for drinks. So our speaker and everybody else will stay.
A thank you for Marta. But that was not actually what I want. So what I said on Open Labs. So I think what I learned is that then we had more or less the idea that we should bring people to the expensive equipment. That's not what you learned me. That's not the way I think forward. So thank you for that. Yeah. So I think I can with trust now say, okay, it was what we did, what we don't need to explore that. But there's one thing that I had in that literature search, and that was actually giving DOIs to equipment. So that was an idea. I'm not sure you said that, right? So. No, it was not. I mean, it was an idea that we shared in the group then, which I thought was actually perhaps valuable, and that's something that you remind me of. So, thank you very much.
Thank you, Wilma. And indeed, now that I'm for drinks, so please go down there in the center of the hall downstairs, just underneath the balcony, there should be drinks set up for us. So let's go on in there and please stay and enjoy a little beverage with us.
Thank you.